In Bangkok for my first time. I'm Benji. I'm a software engineer at Zappy. I'm originally from Cape Town in South Africa, but I'm living in London at the moment. A little bit about me. I love traveling, being in nature, cooking and eating all different kinds of food. So you can imagine how much I'm loving Bangkok. I also love technology, coding, and data. So if you're interested in any of these, come and grab me at the after party for a chat. I'm going to be talking to you today about a fun project that I worked on last year in our Zappy X team, which is Zappy's research and development unit. In this team, we were able to test some weird and wonderful moonshot ideas that we otherwise wouldn't have time to get around to. Before I dig into the project, I just want to give credit to the Chief Innovation Officer at Zappy, Dave Birch, for his leadership on the team and his grit and determination on this project. So this is his brainchild, and it's been a pleasure to work with him and the rest of the team in it. This project is all about a custom data indexing system that we built using Ruby, graphs, and bitmaps. I hope you enjoyed. So here's a quick overview of what we'll be running through this morning. We'll start off with a bit of background information, and I'll paint a little picture about the world before we had the system. We'll then dig into some of the problems that we had, which included how we were storing context onto our data, how we were storing our data, and how we lacked some connection between our data points. I'll then touch on what we needed, and after that, we'll get a little bit technical and go through some of the details around the bitmaps and the graph. And to finish off with, we'll get some performance metrics and architecture overviews. All right, hope that sounds good. Let's get cracking. So at Zappy, we're all about collecting survey data. We have suites of research products on our platform, which hold a collection of questions or surveys. On these surveys, we perform some modeling to get useful insights, which our customers use to make decisions on their advertising. We're usually testing stimuli such as videos or images, and we do the whole thing from ensuring the right people are answering the surveys and are getting rewarded for answering those surveys, all the way down to executing the intellectual property or algorithms through our computation engine, which drive those insights in the charts on our reporting platform. So let's run through what that looks like in our system. So we have got our respondents that are answering questions in our surveys, and these questions get turned into what we call measures. Now, a measure is a digital representation of something in the real world. So I might use the term question and measure interchangeably, but that's just because at the moment we're only collecting readings from the real world through our questions. So these questions get passed into our reporting platform where we do some modeling on the data. This is all done through our in-house computation engine called Quattro. And Quattro essentially allows us to leverage Python pandas through Ruby. This is all so that we can store and perform operations on these measures in the form of a pandas data frame. Our CTO, Brendan, goes into the real reasons why we did this in his talk from RubyConf in 2014. But for me, the only reason is we just love Ruby. So these modeled measures then get stored in our SQL database in the form of a serialized, or pickled, as they call it in Python, data frame. And when our users come into the platform, they can select the surveys that they're interested in, and they can dive into the various charts that we provide. So when fetching the data for these charts, we are fetching the respondent level data from the SQL database, which is mostly pre-transformed or cached. And then we do some additional computation on that to drive those useful insights. The charts allow for filtering, so we can break down how different demographics responded to your stimuli. And they also give us norms or benchmarks so that people can actually get a good gauge on whether things are good or not. So the platform at the moment is incredibly good at this type of analysis, where you know exactly which subset of studies you want to do an analysis on and do some kind of comparison between them. So the architecture is also really good at storing the dependencies behind the models that we're computing, and Quattro is optimized for processing these models and their dependencies. But we want more. We want to query all of our data and in real time. And we also want to store the connections and relationships between our different data points so that we can have a richer data set to provide more useful insights. So nothing So as you'd imagine, nothing is ever that simple when you want to get all the things. So let's have a look at some of the problems that we're facing. So the first problem that we needed to consider is context. When fetching all of the data for something, we need to make sure that that data that we're fetching actually represents the same thing. So the best way to think about this is through an example. So let's consider the case where we want to find out how the brand Yamaha is doing for a particular metric, maybe something like ease of use. So the first problem that we need to consider is context. So when we're fetching all of the data for something, we need to make sure that that data all represents the same thing. And let's think about this example. So we want to find out how the brand Yamaha is doing for a particular metric like ease of use. The question would be, how easy is this thing to use? So if we wanted to write a query for this, we'd say, get me all of the data where the measure is ease of use and the brand is Yamaha. And we'll get this data back and plot the distribution of it. And we take a look at it and we're like, oh, that's a little bit weird. Our distribution has these two peaks in it, which is a little bit odd because you'd expect there to be kind of like one thing that makes it easy to use. And we take a second to think about it and we realize, oh, hang on a second, Yamaha make motorcycles, but they also make pianos. So this could be what's causing this anomaly in the data. So we need to know in what context a given measure was asked in the survey. Was this survey for vehicles or was it for musical instruments? So this additional level of context is key when running a meta-analysis. The next problem that we'll go into is storage. And as I mentioned before, we're storing all of our data in these serialized data frames in SQL. We're also storing each measure on the survey level. So if we run 4 surveys, all with the same measure, we would have 4 separate serialized measures, which would, at the end of the day, need to be concatenated together so that we can get all of the data for that measure. So to put this into some code, for any given measure, we need to iterate through all of the surveys, fetch and deserialize that measure, and ultimately concatenate it together. When you put this onto a database of 10,000 to 100,000 surveys, that's a lot of deserialization and concatenation. So it's pretty slow. And the last problem that we'll look at is the connecting of different data points, something that we call harmonization. Harmonization is all about knowing what data should be treated the same. So we can break down the ways that we define harmonization into 3 broad categories. There's the measure or the question that was asked, the stimuli or the context in which something was asked, and then there's the audience, so who was asked it. This will also be easier through an example. So for measure-based harmonization, we've got 2 questions. Question 1 asked, on a scale of 1 to 10, how easy is this to use? And on another survey, we asked question 2, which said, after that amazing experience, what would you rate its ease of use out of 10? Let's say that these 2 things mean the same thing. So we get this little bidirectional arrow to indicate that these 2 measures should be treated the same. So when we're fetching all of the data for question 1, we should get the data for both question 1 and question 2 together. It's worth mentioning that these actually shouldn't be considered the same thing because the second question is putting this additional bias, saying this is an amazing experience, which the people that have question 1 might not want to include in their results. So we could change that bidirectional arrow to be a one-directional arrow. And now the data for question 2 can include the data from question 1, but not the other way around. So that applies to other types of harmonization, like metadata harmonization. So consider something like this, where we've got the motorbike and the motorcycle categories. We want them to be the same, so we can put these arrows in, and they are the same going forward. So we needed something special, something that will allow us to query our entire data set with both context and harmonization. And it also needs to be fast, real-time fast. So let's just take a step back. We've run through the world before this measure store, and hopefully we have an idea of the types of problems that we were facing. Now that that's over, let's get ready for the cool stuff. Introducing the measure store. And as the Aussies would have named it, it stores measures. I made that up on the spot. I took the other jokes out because they weren't funny. The measure store was built with the core principle that the API needs to be simple and easy to understand. When making requests to the measure store, you can give it three things: the context or the scope, the measure, and the dimensions that you're interested in if you want them. So let's apply that to our Yamaha example. So in this query, we're scoping the query to ask for surveys that have the category as motorcycle and the brand as Yamaha. And we're asking for that ease of use measure, as shown by the square braces. And in this query, we're asking for the same thing, but we're only interested in the people who answered between 7 and 10 by adding those dimensions. Okay, so we've seen how to interface with it. Let's have a look at it in action. So I was going to do a live demo, but I didn't trust the internet here, so we're just going to go through some GIFs. So for the first demo, we're going to take a look at how a particular measure has performed across the different countries that we've run adverts in. So the measure that we're going to look at is ad distinctiveness. The question could have been something like, on a scale of 1 to 5, how distinctive was this ad? And what we'll do is we'll loop over those countries that we've run ads in, and we'll get back the distribution of the measure for that given country. Now, I haven't shown it in the snippet, but we will also draw a little ASCII chart to look at that data. So here's the GIF. It is in real time. And then we run the command. So there we go. It's pretty fast. And for the sake of this example, let's just assume that we want to compare the United States versus the United Kingdom. So here's the data for the United States. All of it came back in 17 milliseconds, which is for 700,000 respondents. We can see that the trend is pretty good. The ads in the States seem to be pretty distinctive. 240,000 people giving it the full 5 out of 5, and only a few people giving it the 1 or 2 out of 5. So it's looking pretty good. Let's have a look at the United Kingdom. And this data came back in only 6 milliseconds, but there's less respondents with only 155,000. And we can tell immediately that there's more measures or more questions with this particular metric in the States. We can also see that the ads in the United Kingdom are not as distinctive as those in the United States. Or the people in the United Kingdom are more pessimistic than those in the United States, which I think is more likely due to the weather. So now we'll take a look at another type of analysis, which involves crossing two different measures together. And this type of analysis is quite popular when you want to see how two different measures relate to one another. So in this case, we'll do a cross between the persuasion measure and the watchful ad measure. So if someone watched the full ad, do they find it more persuasive or not? Watchful ad only has 2 dimensions in it, so it's either a yes or a no. So we'll iterate over those 2 options and do that cross between them. And we run that and get the data back. And we'll take a look at the distribution for those who watched the full ad. And this data came back in 23 milliseconds, and it's doing a cross between 1.5 million respondents who got asked that persuasion question and 1.3 million respondents who watched that full ad. We'll do the same thing for those who didn't watch the full ad, which only took 8 milliseconds, but that's because more people watched the full ad than didn't. They were getting paid to watch the ad, so I'd hope they watched most of it. And we can generally see that those who watched the full ad found it more persuasive. So the last demo that I'll do is harmonization, and a classic problem in this is region. So these are all the regions that we've run ads in the United States. We can see that there's a bit of a translation issue. Some of the studies are in Spanish. So let's harmonize that data so that we can analyze them all together. So we'll start off by looking at the counts of the Northeast region and the Noreste region. Please excuse the pronunciation on that. But there's 360,000 respondents in the Northeast region and 9,000 from Noreste. And we can run this semantic equality command, which is what we use to harmonize data. And we can see in this example that we're setting that bidirectional flag as true. So it's going to go in both directions. And we run that and do the counts again. And here we can see that all the data from the Noresta region is now being included in the Northeast and vice versa. We'll do the same thing for the South and Sur regions and look at those counts before harmonization. And we will do this again, but without that bidirectional command. And this time, we will see that the South, let me just dig into this a little bit more. We're saying that the South should include the data from Sur, but Sur should not include the data from the South. So that's that one-directional harmonization. And we can see here that now the South, when we count those respondents, has the data from Sur and not the other way around. All right, so that is the measure store in action. So we can understand a little bit about how the API works and how to interact with it. But the interesting bits happen under the hood. We can break down the measure store into two key components. There's the part that stores the raw data, and there's the part that stores the context onto that data. So we'll start off by looking at the way that we store the data. And the best way to think about that is as an index with a bunch of columns. So in our application, the index is respondents, and the columns are the measures which get broken down into dimensions. Each dimension is a bitmap. So if a respondent answered yes for a particular dimension, their bit will be set, and if not, their bit will be unset, or 1 or 0. So in practice, we have our 4 respondents over here, and they were each asked the ease of use question, which is on a 10-point scale. So we've got 10 dimensions. Respondent 1 answered a 7, so they'll get a 1 for dimension 7 and 0 for everything else. Respondent 2 answered a 5, 3 gave an 8, and 4 gave a 7. So we can see that in this data set, we've got only the dimension that a respondent selected is true, and everything else is unset. And when we first implemented this, it was really fast to return the data, but the size of the data set grew quite quickly, and we can see in this example why that was happening. We've got all these zeros floating around the database, so the data is really sparse. We found a pretty neat compression algorithm for this called roaring bitmap compression, and this essentially allows us to compress those zeros, so our bitmaps actually look something like this. And now we only need 1 bit to store a single respondent for a particular measure or dimension. So we've got this optimized store to get the data for a given measure, regardless of the survey, no more iteration through those surveys, no more deserialization, and no more concatenation to join it all together. So we're pretty happy. But people do still want to see what their data looks like on a survey level. So let's have a look at how we do that. So we'll add 2 surveys to the mix, respondent 1 and 2, who answered survey number 1, 3 and 4 answered survey number 2. And in terms of the query that we saw in the beginning, these would be part of that scope section. So you'd want to scope on your survey. So we've added the 2 bitmaps, 1 for each of those surveys. And if we want to fetch all of the data for survey number 1 for that ease of use measure, we can fetch all of the respondents from survey number 1 bitmap and all of the dimensions from the ease of use bitmap. And we can do a bitwise AND over those 2 things. And what we're left with are the people who answered survey number 1. And we can do the same thing for survey number 2. The same principle goes with any other measure in our data set. You just do a bitwise AND against each other, and you're left with this filtering effect. So this is how we're storing the data. This is that bitmap store. Let's take a look at how we connect it all together. So initially, when we were talking about the problem of storing the relationships between our data points, we were using a many-to-many Postgres database, relationship in a Postgres database, because we had one running already. But when we started to think about it, we realized that this wasn't necessarily the right tool for the job, because we need something called multi-hop effect, which kind of sounds like something that a graph would be really good at. And to show you what I mean by this, let me run you through the structure of the graph that we went with. So the first node that I'll introduce is the special scope node. And we have a property graph, so you can store your nodes, your edges, and each of those can have properties associated to it. So each scope node has its properties for entity, attribute, value, and its storage key. So in this case, the entity is survey, and this is a survey property. The attribute is category, and the value is motorbike. And we can see that storage key over there too, which is going to point to the location in the bitmap store where that data is stored. We're going to harmonize these things. So we are going to, we also have more data for the other scopes. We've got motorcycle and two-wheel. We'll put an equals edge between them to indicate that they're now harmonized. And now when I fetch the data for motorbike on the left-hand side, I now know that I need to fetch the data of motorcycle and also for two wheels, because even if there isn't this direct link between motorbike and two-wheel. So that's that multi-hop traversal. And yeah, once again, just to reiterate, those storage keys point to the bitmap that represents that data. So the next node that we have is the measure node, and the measure node has a value property which holds the measure's name. And we can scope these measures by adding a scoped edge. So we indicate that this measure has been asked in the context of these scopes. So we're connecting them together. And a measure node needs to have measurements, and these measurements have the storage key property on them and points to the bitmap that holds the data for that measurement. So a measurement would be one of those dimensions in our bitmap store. The measurement node captures a dimension for the connected measure, so we can add these edges to it too. And the last node, I promise, is the constant node, which contains the details of that measurement, which has a value property. So you can see we've got 5, 7, and 8 over there. And these dimensions, these constants, get connected to those measurement nodes, and we can also indicate what type of dimension that is. I know that's a lot to take in, but we made it through the graph structure. If I lost you in that process, let me quickly summarize how it all connects together. So we have the graph with the nodes and the edges that are storing the scopes and measures and the relationship between them. And then we've got the bitmaps that store that raw data. Now, when I run a query in the measure store with the scope of category is motorbike, the graph will go and fetch that scope and all of its harmonized scopes that are connected with these equals edges. And from these scopes, we will take the storage key property from them, which are that pointers to those bitmaps. Next, we'll grab the ease of use measure. So we'll find the measure node that has the value ease of use, and we'll grab all of the measurements that are capturing that measure. And now that we've got those, we can grab their storage keys from their properties. And now we have the location for all of our data that we're going to be running for this query. And we just do a bitwise AND of those two things, the scopes and the measures, and we get our result. So you can see that we're using the graph to determine what data to fetch, and we fetch that corresponding data from the bitmap store. And there we have it, our data index with Ruby graphs and bitmaps. But I haven't mentioned how it's running in production or what tools we're using to implement it. So let me introduce to you our good friend Redis. Because of how compressed our dataset was, and more on this in the following section, we were able to store both the graph and the bitmaps in memory on Redis. Redis has a graph database module, Redis Graph, which is what we're using at the moment to store the nodes and the edges. And for the bitmap store, we're using something called Redis Roaring, which is written by Avigiano. This is also just a Redis module. Now, the measure store gem itself is included in each of our client applications. And in those client apps, all you need to do is configure where the location is of your Redis instance. And the measure store gem will manage the commands that we're going to execute and make sure that we're issuing the right things to Redis. So we've been really amazed by how fast Redis is. So let's take a look at some of the performance characteristics. To give you a rough benchmark for the measure store, I fetched all of the age measures from one of our products where we've got 3,700 surveys. This is a total of 1.56 million respondents. So I ran this on our current reporting platform, which is fetching the measures from each of those surveys, doing that deserialization and concatenation, and the data came back in 90 seconds, which is pretty long for a customer to wait for their chart to load. I did the same thing on the measure store, which is running that scope query on the product and fetching that age bitmap, and the data came back in 495 milliseconds, so a 180x speed up. I also did a quick test to see how fast it could return all of the data for just the age measure, and this took 9 milliseconds, which is for 3.6 million respondents. So that's without having that product scope. And this is so much faster because we don't have to traverse the graph to figure out that scoping business. So to compare the storage benefits of the measure store, I loaded a subset of 40 studies from our existing platform into that SQL database, and they took 3.5 gigs. And then I loaded that same data into the measure store, and the graph came to 23.3 megabytes, and the raw data came up to 4.46. So 28 megabytes for the whole thing. So a 128x compression ratio. So there we have it, the performance characteristics. We were quite happy with how fast it was. So what's next for the measure store? We graduated the project out of its R&D phase in the ZappyX team at the start of this year, and we formed a couple of teams around this ideas that are working on taking those core concepts to production and making sure that we don't lose all of our data in memory. So this is all going to be coming through in the form of a new reporting platform, which our team has been working on for the last 3 months. I'm personally working on the data engine and modeling side of things, so looking at how we can maintain that computation engine on top of this new data storage system. And there we have it. Thanks for listening to me go on about graphs, bitmaps, and data. Enjoy the rest of the conference.